Okay, so last time we looked at robustness in bacterial chemotaxis. We looked at two models. Today I just wanted to quickly go over these and try to implement these using kind of an ODE solver, our common tool, using Jupyter. So just to save on time, I actually did all the imports. These are the stuff we're gonna need. We'll need NumPy. Obviously, we'll need OD, ordinary differential equation integrator, ODE int from SciPy integrate, and matplotlib for the plotting. And again, to save time, I kind of wrote down the equations from last time, from the actual slides, so that we can just quickly go over them. Our differential equation is fixed for both models. It's the rate of change of methylated receptor is methylated by VRR, demethylated by BBB times some binding function for BBB to the methylated receptors. So whether BBB binds binds the receptors in a with a Michaelis-Menten equation, we'll use that. That's what we do in fine-tuned. Barkai-Leibler is the same, but now it's only the active methylated receptors. So this could be any function like we talked about before. It could be any monotonically increasing function of xm. So if we take this equation and rearrange it, we know that the steady state xm with this function applied is always has to be VRR over VBB. That this follows directly from when you make the rate of change 0, move VRR to this side, divide both sides by minus VBB, you get this. So what happens in the fine-tuned model is you put in the Michaelis term here instead of F. So F for fine-tuned is that. And if you solve then for xm steady state, you get this equation which we've seen before, which means at any given point, let's say you already know what the speed of r is, what k is, how much r there is, and you know initially what the speed of b and the amount of b is. You can just plug in those values. So the initial speed of b and all the other constants, known concentrations of b and r, times the initial activity. You can think of this as the input signal, right? So whatever sugar there is, this is essentially inversely proportional to the concentration of the attractant. So if there's more attractant, activity on the receptor drops, because we only have unbound receptors that are active. So if there's a lot of attractant, it binds the receptors and they become inactive. So the initial fraction of receptors that are not unbound, and then you can calculate what some later steady state should be by putting the percent active receptors there. So the signal in the new time, plug in all the numbers, and what the speed of b should be given that level of signal. So if you put these all together and kind of do the algebra, it turns out that if you know the initial speed of b and the initial signal, you can plug in the new signal and find what the speed of b should be at that point. For this, though, we have to assume that r is constant. So we'll call that r tuned. So remember last time we talked about this. Most cells have different levels of r's from cell to cell, and remember, if it has more r, it's somehow more nervous. If it has less r, it's a calmer cell, so tumbles less on average. Even in the steady state, kind of adapts less quickly. If if there's more R, it adapts quicker, and so on and so forth. But we have to assume a single R. That's the kind of the R these cells are assumed to have. Remember that's what made the fine-tuned model a bit fragile, not robust, because that if the actual R is different from R tuned, it doesn't adapt exactly anymore. So we'll start with this and then implement the fine-tuned model, play with it for a few minutes, and then kind of adapt that into the Barkai-Leibler model and see how that does. So we'll start from the input and go all the way down to the tumbling activity. So let me just open a new cell here, and what we're first gonna do is we need some input function. So we'll start with something very simple. Let's say we write a step function, which is a function of time, and it will give us the amount of attractant in the environment at any given time. So if it's a step function, we'll say, for example, if time is less than 200, for the first 200 minutes, there isn't much attractant. So this will return, let's say, for example, 0.1. Else, after the 200th minute, suddenly the attractant jumps immediately into to 0.9. So just to see how this works, let's build a timeline with linspace as usual, and we'll say from 0 to, let's say, 500 minutes. Let's give it subdivisions of 1000, probably overkill, but anyway, let's try that. So the attractant levels are going to be, we're going to basically apply all points on this timeline for t in this increasing timeline of from 0 to 500 minutes. For every time point, calculate the attractant, and that's going to be the list of attractants. Just to make it uniform, we'll also convert this into a NumPy array. And this is the kind of the simple way of doing it, but if you're going to use a function to create new NumPy arrays constantly, there's a method called vectorize. In NumPy, it actually takes a function and makes a vectorized version of that function where you can just directly give the NumPy array you want, and it gives you back the resultant array. So that's the attractant, and let's say the signal then is always 1 minus attractant, because the more, for example, sugar there is, the less activity in the receptors. More of them are occluded or bound, so they're less active. So we define our signal as the activity, and when there's sugar, more sugar, receptors are less active in phosphorylating. So let's plot this just to see how it looks. I'll plot the timeline, and let's plot the attractant. So as we expect, it's going to stay low for up to 200, and then jump up and to 900, and that's the sugar, obviously. The other one, which is our signal, which is what we're actually going to use for our model, is a signal, which, no surprise, it's the opposite of the attractant level. Just to make the math easier and kind of easier to reason about, I'll keep both the signal and the attractant levels between 0 and 1 and kind of normalize them so that we can reason about them easier. Okay, so that was our basic signal. Now let's actually write the fine-tuned model. What I'm going to do is actually probably don't need these anymore. I can just to show you what this does. So I'm just going to get rid of these. And now we have the equations and everything on screen, so it's easier to write. So we'll write a new function for our differential equation, key fine-tuned. So chemotaxis fine-tuned. As usual, remember ODE int. It takes in, you have to give it a function that defines the differential equation system, the initial concentrations, the timeline, in our case, say TT, and all the arguments that function, this function needs. So we'll get to that. But for now, our function again is going to take an array of concentrations as usual. It's going to take the current time. Now, what else do we need for our function? We need all the kind of stuff here. So we need, let's just call them VBB0. We need tuned VRR. And ideally, tuned VRR is the same as VRR, but we know that there's cell-to-cell variation, so we'll also have VRR. Let's actually move this here to the end. So we'll have the initial VBB, that's the speed of B in demethylating at time 0. The current VRR for a given cell, and the tuned VRR, the VRR we're assuming for all cells. Obviously we need K. And we need one other thing. We need essentially the signal function. Let's call it sigfn. And we can, so this becomes pluggable. We can give it a step function, like here. We can give it some other signal function. Actually, let's say for now our signal function is of t is just return 1 minus the step function. Okay, so that's our signal function. I guess that's all we need. Let me see if I missed anything. In order to calculate VBB at any given time, that's what we need to do to calculate. We need VBB. We're assuming VRR is constant, at least for a single cell. We need to calculate VBB. We already know XM from the previous time point. Yeah, that's all I need. So we have VRR, we have VBB, we have VRR but we also need VBB. To calculate VBB, we need the current activity at time 0, which we can find from sigfn. So if we give 0 to the signal function, it will give us the input at time 0, and if we give it give it t, it will give us the signal at t. We need VBB0, so we'll take that from the outside, and we need VRR tuned, which will also be given. I think we are okay. So first thing, the methylated receptor concentration is the first element of this concentration array. We don't have any other elements. We've seen other exercises where you had more than one species. In this case, the only species we're interested in is X-methylated. So now we need VBB in order to calculate the rest. We have X-methylated now. We have K. We need VBB. And it's already calculated here. All I need to do is kind of write that down. So we need input at t divided by input at 0. So straightforward, sigfn at t divided by sigfn at 0. So signal function evaluated at t times signal function evaluated at 0, and then the rest we need VBB 0 minus tuned VRR. Is it? Yeah, okay, so I've done these, this is all okay. All I need to do is also add tuned VRR. So at any given time point, this will calculate what that current speed of B is. Current kind of speed at which it demethylates any given receptor if it encounters it. And obviously this itself would have been governed by a differential equation, but remember we talked about this, that methylation is really slow with respect to phosphorylation, and we're assuming that the moment this step happens at time 200, the sig fn will jump from it's 1 minus, so it will jump down from 0.9 to 0.1, and that will affect the speed at B. Obviously that happens in maybe a few fractions of a second, but we'll assume it's instantaneous because the rest of it is so slow it will seem like instantaneous to the kind of the methylation system. Okay, so we have VBB. Since we have VBB, now we can write this whole thing. We'll return. Again, we need to return an array, but it's an array of one thing, and that's the rate of change of XM. So that's going to be VRR. Notice that this time it's the actual VRR. So if they're the same, you're okay. But if this is a kind of a cell deficient with respect to the average in R, it would be lower. If it's a richer cell, it will be higher. Okay, so VRR minus VBB at time t. So we can actually call this, since we call this VBB 0, let's call this VBBT, so it's more explicit. This is VBBT times f of xm. In our case, that's just the Michaelis thing. So times xm divided by k plus xm. Okay. So no errors there, that's good. At least I don't have syntax errors. So now let's just make up some numbers to make life easier. These will be kind of toy numbers. Let's say k is 1. The tuned VRR is 1. We're assuming that the VRR is kind of that each cell has. Let's say the cell we're simulating actually has that exact VRR for now. We'll play with that later. What else do we need? We need initial VBB. So let's call it initial VBB. So that's what VBB 0 is. And let's call this current VRR. So the VRR you're tuning your cell to, or kind of nature has tuned that cell to, if nature were using the fine-tuned model, and the actual VRR in the cell, and the initial VBB is something we're going to pick as just as a given. And these are all dependent on each other. If you don't pick the initial VBB, then you have to pick the initial steady state and then solve for the initial VBB. It just works either way. We're just going to set the rates instead. So if that's the case, what is the initial steady state? The initial steady state would then be over here, right? It's k times the current VRR. So now we're not interested in the tuned one, but the actual one, divided by the initial VBB minus the current VRR, I think. Yeah. So we'll say the initial concentration array then is, again, since we only have one thing, this initial steady state. Okay. We've already defined the signal here. Maybe we should move this over here, because if we change the thing later on, let's say the signal function is this. Now what do we need? So the signal function is a step function, that's fine. Okay, let's just integrate it. So XM for the fine-tuned model is OD integrate CHE fine-tuned with this initial array. Oh, we need the timeline. So let's say the timeline is from linspace from 0 to 1000 minutes. Let's say 10 subdivisions per minute. Should work. Now that's our timeline. What else do we need? We have the function, we have the concentration, the initial concentration, the time. Oh, we need the arguments. So we give them in the same order here. So first thing we need is a signal function. That's what we call signal, which is kind of an inverse step. So we'll give it signal, and then we'll give it k. So signal k, tuned VRR, VRR, VBB0. So k, tuned VRR, current VRR, and initial VBB. So let's run it. Oops. Extra argument. Oh yeah. Okay. So here it wants the extra arguments to the function to be in a tuple. So we'll just do that to make it happy. Oh, sorry. Forgot the signal. Now it should work. Yeah. So let's plot this. See what it looks like. We'll create a figure. Let's call it fig, which is a PLT figure. And just to make it largish, fig size, let's say, I don't know, 15 by 12 or something like that. 1512 is, yeah, more or less, yeah, it's 5:4. Maybe make it I'll try it. Okay, figure, that's the figure. One thing I want to plot is the attractant first. So again, we'll, like we did before, attractant concentration is going to be a NumPy array containing whatever the attractant function was, evaluated for every time point in our timeline. And what I'm going to do is PLT plot the timeline and the attractant concentration. Let's just give this a color, make it red. Let's see if it works. Yep, and yeah, this is too big. I don't need this big. Let's say 10 to maybe, it's too fat too. So yeah, that looks better. So we have that, but we don't just want to plot the attractant level, but rather how the thing adapts. So what you can do is you can actually plot these on the same plot, but when we change different things, you'll see that the scales will be different. So what I'm going to do is I'm going to plot them as two aligned subplots. So this one will be the first subplot. Let's call it figure add subplot. Funny, the thing doesn't work. So what you have to do here is, I don't know if we talked about this in class, but you give it, so essentially you're creating a grid of subplots, and you have to give it how many rows there are going to be, how many columns, and what number this subplot is going to be. So I want 2 rows, so they're going to be top and bottom, a single column, and this is going to be the first one, so the one on top. Normally if you just run this, you see what happened? It made the top part and the bottom part is missing, which we're going to draw in a minute. So now I can say ax also figure add subplot, this time 2 rows, 1 column, and this is going to be the second one. Now we have the attractant concentration, but what I want, okay, so let's plot this. Plot plt plot. What I want to plot is t time tt, the timeline, and xmft, right? Yeah, that's the thing we integrated. And let's try it. Looks, this doesn't look right. It should come down from here and crash and then recover. Oh, okay, so what we're kind of looking at is just the fraction of methylated receptors. That's not what we want to look at. We want to look at tumbling activity, right? So remember the example in the lecture. So there's light, and then your iris closes, and then light goes away, the iris opens up. So this is actually the control part. Remember that activity is actually this input times how much of it is methylated. So we need to say something like A times XM here, plot that. Because this assumes that there is no change in activity, but what happened here was the signal suddenly dropped down from here, and this is actually compensating for that, so we have to multiply with that. Problem is we don't have an A. What did we name that? We have the attractant concentration, but that's opposite of what we want. So let's call it signal. Signal is equal to 1 minus attractant concentration. So it's the opposite of attractant concentration, except there's a problem here. We name this signal, we also name this function signal. So I'll just rename this. Where did we use this? Signal function. So let's search for it. Oh, let's search for signal. Oh, we use it here. Okay, it's used in the integrator. So let's change this to signal function as well. Let's run it. So I can just say signal. So it's going to calculate the signal as opposite the attractant concentration, and then we'll plot that. Oh, that's not good. Yikes. It's doing a bunch of plots. Oh, okay. So I know the problem here. Let's clear this output. Clear outputs. Now the thing is, now this is an interesting one, but just to debug it, let's take a look at this. What is XMFT? it's this array of things of the level of xm at each time point. That's fine, but notice the shape of the array. It's a matrix with a single column, so it's actually a column vector. So you can actually look at that from the shape. It's a 10,000 row single column vector. And if you look at the same thing for signal, it's this. So we can do one of two things, I think. Signal is an array, the other is a matrix. I wonder what happens if you say xmft flatten. Yeah, it becomes an array. So there's two ways of solving this. You can just flatten xmft, xmft, and let's see if this works. Oh, sorry, flatten. So it takes it kind of down to a single vector, flattens that column into a single vector. We'll see if that works. Oh, it did work, but you have to be careful with this. If you have more than one column, it might go row order or column order, and you might kind of have a problem. One other way of doing this is you can actually take xmft and transpose it, then it becomes a row matrix, and then multiply it with signal. But once you do that, you have to transpose it again, and that should give it the same result. Okay, so I'm gonna leave this at flatten because it's, I don't know, somewhat more explicit what we're doing here. But be careful about flatten. If you have more than one row or more than one column, you have to make sure that you're doing the right order. Okay, so this looks good. Up until 200, you have a little steady state. Suddenly sugar jumps up, and that means when sugar jumps up, tumbling activity crashes down, and like we said, this is almost instantaneous with respect to the methylation, and then kind of methylation decreases until it gets back to the same level of tumbling. Just to make sure that that is the case, I mean, for later when we play with it, let's actually put a horizontal line where the steady state should be. So the steady state activity should be. So the steady state level of methylated receptor is this initial steady state we had here. But the steady state activity is that times, again, the signal, but the signal at 0. So times 0 should be that. Let's see if that actually draws that. Yes, but it's a solid line. What I want is for it to be style to be, let's say, dashed. Yeah, okay. Let's kind of decorate this a bit. Let's give them the axis names. We'll use that later for other stuff. So set x axis x, what was this? X label. Suddenly the autocomplete doesn't work. Okay, let's say that's x label, and y label is tumbling, how much it tumbles. And for the other plot, before we call subplot, if I call these, notice that I'm changing what AX points to when I create a new subplot. So here, this is again time, this is attractant concentration. So let's run this again. Yep, attractant concentration, tumbling, and No, this is y, and that's y. Okay, otherwise I just overwrite the same thing on top. So yeah, time, tumbling, attractant concentration, and this is time as well. So that looks good. Do I need any more decorating? No. Actually, let's make this a bit bigger, 15 by 9 maybe. Okay, let's go even bigger. 20 to 18, too big. 20 to 12. This looks okay. So, just like we expect, you get a step up in attractant concentration, suddenly tumbling stops, bacterium starts going straight, but then in time adapts to the exact same steady state. And this wouldn't really change if I did something else. So for example, what happens if my step was smaller? I could say, instead of jumping up to 0.9, jump to 0.5. Obviously, it adapts much quicker because the difference is less. And since this thing auto scales, you see the whole range, but actually this is 0.9. It goes down to 0.5, whereas when you make it, when you have a bigger step in sugar, notice that it goes all the way down to 0.1. Okay, so but it is faster because it's the same rate. It just has to come back up to this much maybe. So it is robust to the step size, and you can try other stuff. We will in a minute. But it's like what the idea was. It wasn't going to be robust to tuned VRR. Before we get to that, what happens if I change K, for example? I'm going to make it maybe 10 times larger, and if you'd like, you want to pause the video at this point and think about what this will do to the results. And so in 3 seconds I'll evaluate this. 3, 2, 1. Okay, as expected, when you have K is larger, it takes a larger concentration of methylated receptor to actually be active, for BB to be demethylate. So the methylated receptors have to build up more before B can demethylate them in a way. So this thing slows down. It will still adapt though. You can always try that. Let's say go 10,000 minutes. And yeah, eventually it just adapts, but it's slower now. Same thing if you had a smaller K, it would just be faster. So that's what K does in this case. Did I break it? No. So what we were interested in was what happens when you change the current VRR. So let's say our cell, this is like the example in the slides. Let's say our cell has only 80% of what we assume is the right amount of R. And as you can see, the adaptation isn't perfect anymore, right? And because it's tuned to here, and two things happen. One is, notice that the tumbling activity is 0.6. If it were actually that, it would have been at 0.9 because you start at 0.9 and drop and come back. So that would be the actual thing. If it's deficient in R, the steady state tumbling is lower as well, but more importantly, it doesn't adapt anymore. And let's say we also, let's try something bigger. What happens then? It actually will adapt again if you make this large enough, it passes the original steady state, adapts much later. Let's see if that is the case really. Let's look about 10 times more time. Ooh, it's going and going. Let me see. Can it adapt? Let's make this smaller. Yeah, eventually it will get there, but notice that it makes a big difference on where it adapts. And the closer you are to the tuned, excuse me, the tuned VRR, what you assume is true, the better the exact adaptation is. But even something like this, you actually with this you do. Let me make it a bit. Even there you have some difference. So it is sensitive to what current VRR is. So our solution to this was to was the Barkai-Leibler model. Notice that the difference here is this is no longer the binding function is no longer just XM, it's active XM, so unbound receptors. And we said that key B could only, because of the way the thing conforms when it's methylated, could only and it's when it's unbound, can only reach the methylation sites and erase the methyl groups if there was no sugar attached to that receptor. So that's all methylated receptors times the fraction that is not attached by attractants. So this is our signal. The rest is obvious. I mean, you just plug in this function into the initial differential equation, make it 0, solve for XMSS, steady state, you'll get that. And we said that activities should be the same. So activity is this little a times XM, and the activities should be the same at different steady states of different input levels. Should all have the same tumbling activity, and that tumbling activity is X methylated at a certain steady state times the level of 1 minus level of sugar at that steady state. So if we do that at time t, A times the steady state there should be equal to A0 times the steady state there. The interesting thing about this is these all go away. Obviously, since now A is part of the steady state equation, AT cancels out AT, A0 cancels out A0, the KVRRs cancel out. Basically, everything cancels out, and we could get the fact that the speed of B will always be the same once you reach steady state. So you won't have different VBs at different steady states. That wasn't the case here in the phi-tune model. Remember, we had to calculate what the steady state VBB should be once we get to the new steady state after the step happened at time t. So now we won't need that, which makes writing the Barkai-Leibler model much simpler. I'm just gonna actually copy this so I don't have to type it all and not confuse the order of the arguments. So this is key Barkai-Leibler, concentration is the same, T is the same, signal function is the same, K is the same. We no longer need tuned VRR, we just need VRR, and we still need VBB0. Or do we? Oh yeah, we do, because VBB is actually equal to VBB0, so we still need VBB0. So XM is concentration at time 0. Actually, the first element of the concentration area, we only have one element, and then we don't need this junk anymore. And what we need to write is the equation VBB VRR. The only difference is now here you have, instead of VBBT, this is VBB0, because all VBBTs are always equal to VBB0. And what we need here is the signal function function at time t. So sig fn actually gives the value of this a time t. I'm going to use gratuitous parentheses here just to make sure I'm not breaking anything. Times sig fn times xm. Actually, yeah, we didn't need these. Ugly. Okay, so this is one term dividing this term, the whole thing, times VBB0 minus VRR. VRR minus VBB times, yeah. Okay, so that's our Barkai-Leibler. And we can actually copy all this stuff, I guess. It should stay the same. Timeline is the same, signal function can stay the same. Oh, initial steady state is different. So we need a copy of this here. So what is the initial state in terms of Barkai-Leibler is here. So more or less the same. K current VRR, initial VBB minus current VRR, except here we need to multiply this with the signal at time 0, because that's A0. We need the initial steady state. XM steady state at time 0 is 80 times all this stuff. Okay, that's done, and the concentration is the initial steady state. Now we can actually do this. XM Barkai-Leibler is ODE int. Use key Barkai-Leibler. I forgot the other things. Yeah, I'll just copy these. Okay. Concentration 0. The timeline. Signal Fn is the same. K is the same. We have tuned VRR. We don't need tuned VRR anymore. Our only VRR is the current VRR and initial VBB. Okay, let's see if it works. It seems to have. And then we can just copy all this and solve for Barkai-Leibler. Attractant concentration is the same. Signal is the same. Actually, we didn't even need these here. They're already calculated upstairs. Now we plot attractant concentration. Yeah, this is going to be the Barkai-Leibler version of the results. The rest should be more or less the same. Let's see. Yep, looks good. It's a bit faster than the fine-tune model. Actually, what I'm going to do is just to make sure, I played with a lot of things, just to make sure I'm going to restart my Python and make sure everything kind of works from the beginning, since I'm going to upload this notebook to you guys. Okay, everything seems to be working. Now, let's try the actual thing we were trying to do. Let's say V tuned is 0.8. Now, oh, sorry, not V tuned. V current is 0.8. Now, no surprise, the fine-tuned model just couldn't adapt exactly. What's the Barkai-Leibler model gonna do? Perfect. See, it's exactly where it's supposed to be. And you can play with this a lot, and for different current VRRs, even when you make it large, you know how awfully bad the fine-tune model goes. Barkai-Leibler should not be affected. This just happens to be a nervous bacterium. Okay. So this is the basics of it. But before we leave it here, I just want to show you one other thing. Let's collect all of these and make a very simple simulator. So I'll say, okay, how are we for time? It's almost an hour, so let's do this quick. We'll say this is our simulator, and all I'm going to do is wrap up everything we did up to now into one function called simulate. So for simulate, we will have some attractant function, and then we'll have a horizon, which is the maximum time we want to simulate to. Initially it was 1000, so we'll leave that as 1000. We'll have a VRR that we assume, which is 1.0. I'm just giving these default values so I don't have to change them if I don't need to. We'll assume an initial VBB, and we'll assume a K. So then we'll just copy everything from here. First thing we need is the timeline. So it gets copied down here, except it's now up to the horizon, and it's 10 times whatever the horizon is. So it's variable. Now we can change how far we look. We don't have to look to 1000. The second thing we need, let's calculate the attractant concentrations in the signal for, let's take this thing. So whatever is given, we'll create a new signal function based on that. Now it's no longer step, but we're going to give some function from the outside. It could be step, it could be something else. And let's take, attractant concentration, and so we have both a signal function which calculates what the signal should be at any given time, but also a signal array which is pre-calculated signals for each one of these times in TT. So we need both, because when you're plotting you need this array to plot, but when you're using the ODE integrator, it expects to give a time and get a result back. Okay, so we did that. So let's draw the figure. Let's create the figure first and draw all the attractant concentrations. So this function, when I run it, will do all the stuff we kind of did step by step all at once and run the whole thing and show us both results. So I drew the attractant. So the first part I wanted to draw, and this is no longer a 2-row array, but a 3-row kind of grid of plots. Now we're going to draw 3 plots one after the other. First one is going to be the sugar, how the sugar changes. The second one will be the fine-tuned model, and the third one will be the Barkai-Leibler model. So let's do fine-tuned first. I'll just steal my own code from here. Fine-tuned, what did I need? I need all of this stuff. So the initial steady state for fine-tuned, now we have to give them other names because there's going to be 2 initial steady states, one for fine-tuned, one for Barkai-Leibler. Yeah, we'll change these as the current VRR is basically VRR. And initial VBB is just VBB0, and current VRR is VRR. Okay, What about our tuned VRR? Okay, we'll deal with that when we get there. So we got all that. We already have the timeline. We already have the signal function. So I'll just take this integrator and have it integrate over here. Yes, it uses key fine-tune 0 signal fn was already defined inside this function. K is defined. Tuned VRR. This is a problem. So we can either give a tuned VRR from the outside. Just keep it simple. We'll just assume tuned VRR is 1. And we'll be able to change this VRR and see what happens. You can always just do this, like give it a separate tuned VRR argument, but I mean, you get the idea there. It's 1, we'll change this one to see how it fails to adapt from there. What am I missing? Actually, I'm just gonna add it. Let's make it be complete. So that's the tuned VRR. We probably won't use it. That's what we're gonna do. And since we've done the fine-tune model, we'll just steal this part and have it plot that. So this one, and say call this also set title fine tuned model. If this works here. It does. What I did wrong. Okay, so we'll do that. The only difference now is this is not correct. This is initial steady state for fine-tuned now. Therefore, this is concentration 0 for fine-tuned. And what else? Signal FN, the rest should work. Again, this is initial SS for fine-tuned. I am looking for trouble renaming things on the fly. Okay, let's see if the simulate works just for fine-tuned. Simulate with a step function, which we already have conveniently, and don't change anything else. Yikes. We forgot something. What did we forget? What's it doing? Starting from 0, but then jumping up. Forgot to rename something, definitely. What did we forget to rename? Oh, these things. Yeah, forgot to rename this. Tuned VRR is VRR now. Oh, sorry, that's still tuned VRR. Current VRR is just VRR now. And you see what's happening is it's capturing the old variables from the outside, which actually, to make this all very easy, let's just restart the kernel so there is nothing for it to capture. Now let's run it, see if we still have problems. Name step is non-defined. Yeah, because it actually does need that. It also needs the fine-tuned function. That should be all it needs. What is missing? NP. Oh, forgot to import the stuff. So import that. Now it should be happy. Yeah. And it seems to be working just fine. Okay, so this is no longer a plot with two rows. It's 3 rows now, so that's why this is too thick. And run it. Okay, now it's good. This time is getting let's say the attractant doesn't have a time. This is time from the bottom here. So that's the fine-tuned model. We'll actually say that, and now we steal from Barkai-Leibler. We'll get these, rename everything. So the third figure is going to be this, the third subplot. This is going to be now BL, Barkai-Leibler. This is going to be Barkai-Leibler as well. This is going to be VB0. This is going to be VRR. Again, this is going to be VRR. K stays the same. And this is going to be Barkai-Leibler again. That's about right. This is going to be Barkai-Leibler function. This is on the inside, it's called VRR, and this is called VBB0. Okay, that's done. And let's add the other subplot here for Barkai-Leibler. Yes. So this is the Barkai-Leibler plot. Okay. Now again, 3 rows. This is the third one. Barkai-Leibler signal times Barkai-Leibler signal is the same. That's no problem. This is going to be initial steady state Barkai-Leibler. Should work now. I don't know. Let's see. Step. Yeah, we need that as well. We need to try it. Okay, looks good. Let's see if it actually is doing it correctly. 0.8. If you simulate with that, yeah, the fine-tuned model can't adapt, the other one can. Actually, let's also give that plot a title, which is going to be Barkai-Leibler model. Okay. Now, the reason I did this whole thing is now we can play with it easily and change different, give it different inputs, and you can do the same at home if you download this notebook later on. But there's just a couple of things I want to show you. One is, let's see what happens with a pulse. So we'll create a pulse function again, which will be dependent on t, and that t is going to be if t is less than 200, return 0.1, so the baseline level of sugar. I don't need an else, because if it's true, it will just exit here anyway. If t is less than 400, then return 0.9, for example. And if t is less than 600, or rather, if just go back to 0.1. So from 0 to 200, 0.1, from 200 to 400, 0.9, and then it goes back. So it's a step up and a down, so it's a pulse. That's what we did, and now you can just simulate with a pulse. Ay, what did we do wrong? Let's see. This is not a pulse. We forgot something here in the simulate. thing, we forgot a step. Attractant function, let's search for step here. Oh, there you are. This is the problem with copy pasting code and renaming everything. So now it should work. Okay, see what happens? When sugar jumps up, they start tumbling less, both of them, and then they adapt, and when it comes back down, they readapt. This is kind of quick, so let's slow it down a bit. Let's make k is equal to 5, so you can actually see them doing this. And Barkai-Leibler is a bit quicker in adapting. I don't need the time here either. It's colliding with the other title. You can probably put extra gaps in the middle, but okay, so that's the thing. What if though this is kind of this type of pulse, etc., is good, but it's not natural. And notice that at this point, this thing is not actually differentiable technically. So you get funny behavior. What's much better, if you want to try it, is to use a pulse that's more kind of soft, right? Something like a bell curve. For that, we can actually use SciPy stats and make a Gaussian pulse. We'll import that. Actually, let's import it first because I don't remember the thing. So def, let's call it Gaussian t of t. So return, I want it to return SciPy stats. What was this called? Norm? Yeah, norm. Okay. Norm, SciPy stats norm. Location specifies the mean, scale specifies the standard deviation, and what we need is the PDF, the density function. That's the one that's that nice bell curve. So you can say norm.pdf, calculate the probability at t for location, let's say at 500, so the middle of the timeline, and scale, let's say 50. It has a standard deviation of 50, so it should roughly give us a pulse of width about 100 minutes, but it's software, so we'll try that, and let's see what happens. So we'll fix this k back, and let's look at the Gaussian. Okay, now this is interesting. See what happens? Low sugar, low sugar, low sugar. The bacteria are happy. They're just tumbling along at their steady state. And at one point, suddenly, actually this is, let's, just to make sure that this isn't what I think it is, let's just add 0.1 to this. Oh, 0.5. Yeah, that's the problem. We shouldn't have negative tumbling. But it does happen. Anyway, we'll figure that out later on. It doesn't change the dynamics. Suddenly, sugar starts increasing. They say, okay, we're getting warmer. Let's not tumble. Let's go straight. And sugar increases. They they adapt to that, but it keeps increasing. So they tumble less, tumble less, tumble less, tumble less. But at that point, somewhere here, the derivative of the change of the sugar, if you notice, it changes, so it's flattening out. So they tumble a bit more, and after the peak, suddenly sugar stops dropping and panic. So same thing for the Barkai-Leibler model, same thing for the fine-tuned model. So what happens when you can't adapt exactly? Right now, we're tuned VRR is the same as the actual VRR, so these two are equivalent more or less. What happens is, what if I give it a VRR of 0.8? When I run this is what happens. When you adapt exactly, you're still good. When you can't adapt exactly, you're basically your behavior is inefficient now. As the sugar increases, you're tumbling less, but then you only react not to the small changes, but when there's bulk change in sugar, then you decide to tumble more and more, but by that time you missed the sugar. Think of this like the worm web example where, actually let me just open that up. Remember? So this circle here, if you assume you look at it from the top, you're basically looking at this sugar gradient, right, as you move. So again, when there's adaptation, but it's not exact, they generally do the right thing, except they're not very efficient at it. However, if you can react immediately when the gradient is getting shallower, or worse, when you pass the top point, you're much faster at reacting to and kind of finding the optimum, the place where there's most sugar. Okay, so that's the idea here. You can try it with other things as well. As an exercise, try to, for example, build a ladder as a pulse, see how the models work. I think at one point I tried a sine wave, and you can actually look at what happens when you change the frequency of the sine wave. Obviously, it doesn't. You rarely get kind of sinusoidal input in biological systems unless it's done by humans, at least at the cell level. But kind of, it's an interesting thing. It's kind of the frequency. You can measure the frequency response of the system and how it reacts with when it's able to adapt exactly versus not, right? So here's the same thing with exact adaptation. Okay, I think I've run long enough. It's almost an hour, 15 minutes. If you have questions, just let me know.